Welcome to the Connect with BMC Helix ITSM and Remedy webinar. Today's topic is on Java performance monitoring, and Hugo Vuong will take us through this content. Over to you, Hugo.
My name is Hugo Vuong. I'm with the BMC performance team. For the agenda, we're going to discuss the goal. I will state the goal and the objective, and we'll talk about it a little bit. This goal is divided into three sections. The first one is JVM runtime data, and this includes monitor and collect of the data, and then understanding and interpret the data. The second part is typical JVM behavior of the AR server and the web tiers, and we're going to include the mid-tier and the smart IT for the discussion. And the third part is troubleshooting essentials. This will contain mostly the use cases so that we will have some context to understand and interpret the JVM data that we encounter every day. So the collection of use cases are those that I've filtered out from my experiences working with different customers over the years. And then, of course, there's the references at the end in case you need to look more things up. Okay. So for the goal, performance tuning for the ITSM stack from the perspective of the JVM. So without talking about it too much, the statement itself implies that there are other perspectives. For example, you can look at an application running and you can see the process from the OS perspective. So you can, of course, fine-tune the process itself from the OS perspective. Okay. But what we're going to do is to look at this from the perspective of Java JVM. That's the Java virtual machine. So before we can fine-tune or analyze or anything, of course, we need the data. So we will talk about the tool for collecting the data and why we've chosen this tool, of course, how to configure the tool, how to start and to monitor and collect and save the data for analysis, and then how to apply that in a production environment. Of course, you're free to do that for your pre-prod environment too. But the danger in doing the monitoring and collecting in a prod environment is that will this impact the performance of the stack? And we will talk more about that. Okay. So as with any process, the first thing that allows us to look into the process itself is instrumentation. Now, fortunately, Java comes with instrumentation already built in. Now, to access this built-in instrumentation, there are two mechanisms. One is through the attached API, and this is done via the local inter-process communication. And by inter-process and by local, what we mean is the tool doing the collection interfacing with the instrumentation is running on the same OS, on the same box as the Java process itself. This is what's meant by local inter-process. The other mechanism is through the JMX, or Java Management Extension protocol. And this is a remote service. And most of the time, this is what we're going to do. And the reason for that is very straightforward. At the end of the day, for a production environment, we will be monitoring probably at least 20 different Java processes or Java targets. I would just say JVM target or Java targets. These are synonymous. And it's not really feasible to run the tool on every single machine that these Java targets are running. That's one. And the other thing is, well, when you run the tool on the same box, same OS, same machine, if the Java process itself is suffering some type of resource limitation, by running the tool, you will exacerbate that condition. So it's not really a good idea. So most of the time, we'll be going through the JMX remote service. So what this means is, well, when you have a Java target or a target JVM that you want to monitor, you need to turn this JMX service on. Well, you say, well, why shouldn't Java turn that on, for you already? And the answer has to do with security. When you turn this on, you are allowing a remote process to examine what's happening inside your Java. And it can do more than just examining the inside. Like, for example, you can take thread dump or heap dump. And when you take a heap dump, if you are running with a 20 gig heap, that will basically just freeze your target JVM because it has to write to disk 20 gig of data. So it's very dangerous. So by default, it's not turned on. So what this means is you need to turn on this remote JMX service. And to turn this on, there's this 4 lines that you have to add to the JVM org. First, you say, well, turn on the remote JMX. And then second, you need to select a free port, a free and available to you to use. Especially when you have firewalls, right? Not all ports are available. So you need to do a netstat to find a port that's available for you to use. In this case, I gave an example. It's 8088. But basically, just put a port number there. And then most people monitoring remotely through the internet would want to have SSL on and some type of authentication on. Well, for the purpose of this talk, we want to keep everything simple, so I have that off and authentication off. So don't do this in real life if you have a production environment and you're monitoring from the other side of the world because, well, it's very dangerous. Okay, so don't do that. But with everything, if you want to know more, you can always Google more on this, okay? The last part is that, you can turn this JMX on programmatically. And how to do that? Well, the application running on top of Java can turn this on. Okay. Now, the reason why I mentioned that here is because for the AR server, it's already turned on for you, and the default port is 61500. Well, the meta question, which is most relevant, is, well, is that on also for the mid-tier or the Smart IT or any of the plugin servers? And the answer is no. You kind of have to turn that on yourself. And the reason is this. Think about mid-tier and Smart IT. Those are web applications. So web applications are hosted in a web server. And most of the time, that's a Tomcat. So really, it is the Tomcat that is the application, not the mid-tier or the Smart IT. Okay? So what that means is, if you want remote monitoring on, you need to turn this on manually. So just keep in mind, only the AR server has this turned on by default, and it runs on port 61500. And then this talk is very basic. There's no coverage of virtual network or Docker node, for example. So you can go ahead and Google for all the events. Okay, so let's examine what we've covered so far. If you have, let's, for this moment in time, keep to one target JVM. You have one target JVM running, and you want to know what's going on inside this target JVM. Well, you have two methods. One is local, and the other one is remote via JMX. Okay? Local is dissuaded. Okay? Try remote. because as I mentioned, the resource contention issue with logo. Well, once you have the instrumentation turned on inside the Java process, then you need some tool to interface with that instrumentation. And the tool here is the jvisualvm, or if you don't have the full JDK install, you can download this separately. I think nowadays most people just install the JRE to minimize the footprint and security issues too. You can just go ahead and Google Visual VM download. And when you do that, it will show some link and you can download this, and it's a separate application. Otherwise, you just go into your JDK, wherever the install is in the bin, there's jvisualvm. Okay, so that's the tool. And the reason why I chose this tool and work with this tool over the years is because it's available with practically every customer, because every customer would have a JDK installed somewhere. So I would just go in and use that instead of having to download a separate tool. It's very, very convenient. And it's free, so no licensing fee or anything, no license transfer. Only part that's important about this tool is when you launch it, the default is for this tool to collect and cache only 60 minutes of data. Most cases, 60 minutes might be enough, but for some cases, when you have intermittent occurrence of errors or slowdown, 60 minutes may not be enough. So I always advise all the customers to change this up to 24 hours. So I am going to show you that in the demo. And then I'm also going to show in the demo how to add multiple targets, JVM targets, to the tool, and to start the monitoring and collecting and saving of the data. Okay, so let's go one things first. For the note down there, the reason why I added that note is this. In a production environment, let's say in the lab when we do a benchmark, sometimes I have to monitor 20 JVM targets. So it's nice to have one client to be able to monitor 20 targets because I have everything in one place and I can look at that. Now, the opposite is also nice. If you have one JVM target sitting somewhere, sometimes I work from home, sometimes I'm in the office, so I start two clients, one to monitor from home, one to monitor at work. And that's kind of nice too, because then, the client can run and collect the data in the background, and I don't have to really worry about it. Okay, so remember, when you start one instance of jvisualvm, it can monitor multiple JVM targets. That is the common use case. But the one that's not so common is that one target JVM can be monitored by more than one client. My suggestion is to keep it to two. And there's a reason for that when we go into production, right? So let's talk about production, the second bullet item, and then we'll return to the first one. So in a production environment, as we speak, I have many customers that have the monitoring on 24/7. And I have put on here that there's almost no overhead. So the question is, really? Well, there's a reason for this. The instrumentation is actually quite minimal. And here, it is the tool that's doing all the data aggregation and collection, caching, saving. Everything is done by the client side. The target JVM, the most you can do, or the most the client can do, is ask the JVM, what's your status at this time? Okay, what's your status this time? And that's basically it. So one target JVM can accommodate as I mentioned, one or more JVM clients. In a production environment, try to limit that to 2. So in my case, it's one's at work and one's at home. And the reason for that is, let's say you have one target JVM and you have 10 clients asking for data. Well, that's going to put a load on there. With 2, it's not so much. But as you increase, you'll put more and more stress on the target JVM. So you want to keep that to minimal. So for production environment, I advise to have that at 2. Okay. Now, to take a snapshot, you need to know where the nav tree is and how to right-click and take a snapshot on that, and then how to save it. The best thing is for me to do a demo. If you miss some portion of this, no worries, or if I go too fast, no worries. That's another reference. I think several years ago, I did another video on how to do that, and that one, that's the reference right there. And so let me go ahead and do the demo. I'm running JDK 1.8. So what you need to do is go into where you install the JDK. In the bin directory, there is jvisualvm exe. And when you launch that, this is what you see. The first time you run it, you'll see a start page. And this will be checked, show on startup. I never want to see this because I use this all the time, so I don't really look at it anymore. But it has linked to your Visual VM home. And getting started Visual VM, I think the second and the third one are important, because if your first time using this tool, it's good to read some context and really some how-to. And this troubleshooting guide really helps, especially if you have like firewall, etc. So since I don't need this anymore, I'm just going to close it off. And this is what you see. All right, let's take a look at the nav tree here on the left-hand side. So you see that under local, remember I mentioned that there is the interprocess mechanism. So on my local machine, I have Visual VM, which is this tool itself is running, and it's Java. So it will show up. And then you can see here that I also have Eclipse running because I'm doing some development, and that shows up because that is also Java. Now, for remote, I don't have anything, okay? So I'm going to start adding some stuff. There's a machine that I have running. So to add the host, wait, hang on. That's true. I need to show you how to configure the tool first. So the only thing that you need to do with this tool is go into Tools, Options, and here in the monitored host, if you run it the first time, it will say 60, which is 1 hour. My only suggestion to you is to change everybody here and here to 1440, which is 24 hours. You can ask, well, what's that monitored host, threads, and monitor data? Well, monitored host is how often it should ping to see if the host is alive, and the default is 3. I kept it at that. And for threads, data, and monitor data, that's 1. That's the default. I kept that at that. Okay? So let's go. So for remote, what you need to do is you need to select in the nav tree, right-click, and then add your remote host. So I have one machine that's running right now. So when I add that, there it is. Now, on the single machine, there may be multiple JVM targets running, okay? Remember, for those JVM targets that you want to look inside of, you need to turn the JMX protocol on. And when you do turn it on, you need to pick a port that's available. Now, let's say you have 3 JVM targets, then those each of them need to run on a different port, okay? And the reason is that those are services, so each service has to run on its own port. Now, I'm just going to do one for simplicity. And so I select, right-click, add JMX connection, and as I mentioned, the default port for AR server is 61500. And I just happen to keep it at that. So I put 61,500. Okay. Now, if it's a real AR server, you need to use the credentials. You need to use the app admin and the app admin password. But since it's my fake environment, I don't have anything, so I'm good with that. And I think as of 1902, the AR servers does not use SSL connection. Let's just say OK, and it will show up here. Well, it will take some time. Okay, there it is. So now to start monitoring, all you need to do is select it and then double click. Here it is. Okay, so what you really want to see is this. So this is the overview. This is the monitor. So when you click on the monitor tab, it will show you 4 charts. This is the CPU, the current CPU usage. And the blue is GC activity. There's no GC activity right now. And then this is the current heap usage. And this is current threads. Now, over here is classes, number of classes loaded, and so on. I don't really use this too often, unless there's a need for it. And you can say, well, when do you use it? Well, sometimes customers write their own custom code, and it includes a lot of Java classes and have issues with it, then I would use this. But most of the time, I just use these 3 charts here. Okay, so how to take a snapshot. So now remember, for one remote machine, you can have multiple JVM targets. Here, for simplicity, I just have one JVM target. To start the monitoring process, just double click and we'll start. So since the monitoring and data collection is client side, you need to leave this tool running, because the moment you exit this tool, everything's gone. Remember, the target JVM will not have a history, because the best it can do is answer your question, what is your status at this time? And that's it. Okay. So you need to leave this tool running. And when it runs, it will collect and aggregate. And since I've configured for 24 hours, it will just collect 24 hours worth of data and aggregating that for me. Now, anything that's older than 24 hours will drop off on the left-hand side. Okay. So now to take the application snapshot for this particular target JVM, just right-click and say application snapshot. And when you do that, it will show up here in the archive. And then also it pops up here. Okay. And notice the difference here. Here, the time is static. Nothing is moving, because this is a snapshot up to that instance in time. Here is live monitoring. So you can see the time is clicking away. Okay. Now, since this is for demo, I don't really want to analyze this moment in time. I'll close that off. I'll go here. The first question is, well, where is that snapshot? And the answer is, who cares? So what you do is you right-click on this and say Save As. And then now you can pick your favorite location and then save it there. Give it a good name, like for this instance, AR server 10 or whatever, and then the date so that you will know. But here, I'm not going to put it anywhere. But for you, save your favorite location, and then you can go there and get it. Okay? The next question I want to answer is, well, how big is the snapshot? All right. The answer is not very big. So for a 24-hour snapshot, it's roughly 2 megs of data. And this is really, really nice, because when I work with customers, they have to upload snapshot to the ticket, and I download all that. I just don't do that really often. I just talk to the customer and say, why don't you monitor for the next 15 minutes? Take a snapshot and email it to me. And in 15 minutes, the snapshot will be like about 25 kbyte or something like that. So it's easy email attachment. First thing, jvisualvm is a client-side monitoring. And what that means is it's the client, the client application itself that is doing all the data aggregation and data collection. And at each second in time, it asks all the target JVM, say, what's your status? And it collects and aggregates that data. Okay. You can use this in production environment. And remember, in production environment, try to keep 2 clients per target JVM. That's my advice. That would be good enough. Then you don't really impact the performance of the production environment itself. And then lastly, if you have, if I went over anything too fast, you can just go here, and this is like an hour video, and then you can check that out. So now that we know the tool to use, configure the tool correctly, how to start the monitor, collect the data, save the data, we want a basic skill set to working skill set, really, to start understanding and interpreting the data that's collected. And so this is divided into 3 portions. The first part is all about CPU and GC usage. If you recall the tool, there were 4 charts. This is the upper left hand chart. So I'm moving in a clockwise direction. And then moving to the right, we have the heap usage. And then moving down, you have the thread count. And then remember the lower left-hand side, there was the number of classes loaded. And I mentioned that I don't really use that too often. So these are the 3 topics that I'm going to focus on. Here, this is upper left-hand side, the CPU, and this is GC, the blue portion. This on the right hand side here is the current heap usage. You can see the orange is the free and the blue is the used. And then bottom you see threads. The orange here is the number of live threads and the blue is the number of daemon threads. We want to have a basic working skill set. So what about CPU, right? So I want to make one distinction first. If you're running a Java application that only you yourself use on your own machine, then, well, if it takes a little longer to do something, it doesn't really matter, right? It's only you who's waiting. But if you're running the Java application as a service, servicing hundreds or thousands of users, well, if you take too long to do something, it's not acceptable. Okay, so that's the main difference. So the following rules that I'm about to discuss applies to when you're running Java application as a service. Okay, so well, someone asked me this meta question. Are the rules good for just the ITSM stack, or can I apply this rule to other Java service applications? And my answer is, well, I want to say ITSM stack, because this is based on my extensive experience working with the ITSM stack. But I would imagine that this set of rules would apply to any Java application running as a service. So if you have a product from another company that's running as a service and you have slowdowns in user service, you should look over these slides. They do apply. I would say that I'm fairly confident that this is also true in other Java applications. Okay? So first thing, CPU usage. What do we look for? So first rule is that you don't want the CPU usage to exceed 80% mark for extended period of time. And the question would be, what's extended? And here I put down over 30 seconds. So there's another paren after that. And the paren says, if so, service time is not optimal, but do check for jump in live threads. Okay, so remember, your application is running as a service. So when there is a slowdown, then you see any good service would begin to queue up requests or service requests, right? So when it begins to queue up, it will need to create more threads to begin to service the queue. So when that happens, you will definitely see a jump in the number of live threads. So what am I talking about? It's the lower right-hand chart. I will go back to that soon enough. Okay. Second, what about GC usage? How much is too much? Okay, and how much is appropriate? Well, this actually has a very straightforward answer. Your GC should be below 5% almost all of the time. It is okay to have a GC jump during a major cycle. Well, of course, someone will ask me, how do I know if it's a major cycle or a minor cycle? And what is a major or minor cycle? Oh, that's beyond the scope of this talk. But the only way for you to know for sure between a major and minor cycle is to look into the GC log. But you can fairly accurately guess between a major and minor cycle just by looking at the pattern of the heap usage chart, and I'll go into that. So for minor cycle, you see like a sawtooth, and for major cycle, you see that there's a big drop in the heap cleanup. Okay, we'll go there soon enough. So 5% is really the key. Okay, now when you do have a major cycle, how long should that last? Well, you should always shoot for 3 seconds or less. And then someone will say, well, what does that mean exactly? Well, just imagine this. Say for simplest case, just imagine a web application. A normal HTTP request comes in, let's say it gets serviced in half a second, okay? Because it requires some data transfer there. So if the request comes in and a major GC cycle happens, and the GC cycle happens to be 3 seconds long, then for that particular request, the total time for service would be 3.5 seconds, because during a major GC cycle, everything stops. Okay, all the services stop. So is that acceptable? The answer is, well, if it happens once in a while, it's okay, because guess what? For the internet, there's fluctuation in terms of bandwidth availability too. So not so much. But 3 seconds is a good rule to have. Anything longer than that would be too much. Okay, so if there is a jump in GC usage, you must look into the heap to see that there is a heap reclaim reason. If there's a jump in GC usage, but there's no reason for that, then you should really look into that. And how do you look into that? You have to dump out the GC log and then examine that log. And that's beyond the scope of this talk, but you can also Google to see how to analyze GC logs. Okay? So here's the note. JVM snapshot is insufficient to do GC analysis. You really need the GC log for that. Okay, so moving on to the heap. Okay, so for the heap, for Java, you can start Java with 2 different types of heap allocation. If, by the way, the -ms starts for startup heap amount, and MX stands for maximum heap amount. So you can do what's called a range allocation. A range allocation is the startup value less than the max value, and a fixed allocation, which is when the startup value is exactly the same as the max allocation. So why the difference? Okay, so for heap usage, fixed is preferred and higher performant. And the reason for that is you start the Java process up and you tell the Java process, hey, this is everything there is, and it's up to you to manage this. Okay, and Java will do a pretty good job at doing that. Now, for range allocation, you start up and you say, oh, here's something to start, but if you need more, you can ask for more. Okay, and this is how much more you can have. That's the max value. So as the Java process runs, and it needs more, would ask for more. So first thing you notice is fragmentation of the heap, because it's no longer contiguous, because the moment Java asks for a memory block, it's up to the OS to allocate the memory, right? So it can be anywhere. So that's one thing that it will be a performance hit, is fragmentation of the heap. And sometimes the heap can be so fragmented that even though the monitoring data says, hey, you have a gig available, and then you try to allocate 100K for an object, and it says out of memory because you have no contiguous portion of 100K. Okay, so then you say, well, then why don't you just use fixed allocation all the time? Why allow people to use range allocation? Well, it turns out that range allocation is good if you know known memory usage pattern. So for example, if you have the AR server running, and the AR server runs, let's say, one plugin server, let's say for the purpose of discussion, the FTS plugin. Okay, so request comes in for FTS. Remember, the CPU usage follows the data, okay? And the data itself moves. So, for example, FTS comes in and say, hey, look, there's this 4 characters here. Do an FTS on that. The heap usage for the object and creation of this request will use some heap. So first, the heap usage happen in the AR server, and then the AR server then shoots that object over to the FTS plugin. Now it's free, so that goes into garbage collection bucket. So the object then goes over to the FTS plugin. So now the heap usage for FTS plugin goes up. Okay, and then CPU goes up to process that request, and then says, oh, I'm going to wrap this up in an object, and shoots it back to AR server. So then all that memory is now go into the garbage collection bucket. Well, it goes into garbage collection bucket doesn't mean it's available right away. You know that, right? It means that in the next garbage collection cycle, it may or may not be cleaned up and become available, right? Depending on major or minor cycles. It doesn't matter. So the heap then goes up in the AR server because it has to receive the object has to go into the heap, so the heap usage. So you can see that the heap usage pattern staggers. You know, there's heap usage in AR server first, then it passes over to the FTS plugin, and then FTS plugin does all the work, then the heap usage goes back to the AR server. In some cases where you know of the memory usage pattern and memory availability is a concern, then you can use the range allocation. But most of the time I say, you know what, put some more RAM in it. That's what I tell the customers. But sometimes they say, well, easy for you to say if it's just one AR server, but we have like 20 AR servers, and the cost becomes prohibitive. But in any case, use range allocation when you do know the usage pattern, and use a fixed allocation for higher performance. Okay? So now, because a range allocation means the heap will go up and down. I can't really talk too much about the percentage of that, but for fixed allocation, look at the third bullet point now. Fixed allocation, the heap should have at minimum 1/3 of the total memory available for as working memory, preferably half of it. So you can say, well, can you show me a graph so I can visualize it? We'll get there. So what this means is, if you picture, remember the orange line shows the total heap availability, and the blue line shows the heap amount used. What you want to see is the blue line, the distance from the blue line to the orange line, to be at least 1/3, but preferably 1/2, so that way you can have a lot of room for a Java process to work. Okay. Now moving on to the threads, we will go back to the demo and the chart. What you want to see is the thread count should be fairly stable. And what I mean by fairly stable is the fluctuation should be about 10%. Once the Java process, remember you're having server-side Java applications, so there are a lot of threads running all the time. I mean, the heaviest usage, I've seen like about 4,000 threads on a Solaris machine. Okay, so you want to have that number fairly stable. Plus minus 10% is good. But if you have a jump larger than 20%, that's not good. That would really, it's a good indicator for a slowdown in service time. Okay, so now last I just threw this in because this relates to the AR server. You know that we have this KA, and it says that for your Java process, based on the number of CPU allocated, the fast and list threads should follow the 3 and 5x rule. Okay, so I threw that in just for that. When you look at this, it looks really busy, and you say, "Whoa, Hugo, look, it crosses the 8% mark a lot of times." How long is that? Well, kind of tough to tell, right? But the good part is that you should be able to zoom in. Okay, you can click on this and zoom in. Let me hold off for a second. Look at the GC here. You say, wow, that's a GC jump right there, right? The blue is GC. What's the reason? Well, again, we can zoom in and take a look at that. But what you really want to see is when there's a GC jump here, corresponding to that, the heap, there must be something happening over here, okay? But when you have a GC jump like this, and you have a thread jump also, well, and the jump is more than 20%, you better go and take a look at that, a closer look at that. Okay, so let's go now. So the main purpose of this demo is to show you what's called the granularity of the graph, the chart. When you do a charting package like this, and you put in a lot of data, it has to pick and choose. Like, oh, every 100 point, I will put a I'll mark it, and then I draw a line, right? So you know right away that when you load a lot of data and you have this view of all the data, it's not going to be that accurate. If you want accuracy, you need to pick a point, let's say here, at 5:33:04, and then drill down on that. So let's go ahead and do that. So when you click on this, and then you can zoom in. As you zoom in, you see the chart redraws much better. Okay, so let me zoom in. Okay, this was the point of interest, 5:33:04. Look what happened here. Okay, so the point before that was 5:32:53. Okay, so from here, and you say, well, what's the straight line? A straight line is when this tool asks for data from the target JVM and it's getting no response back. So remember, every second it asks the JVM, hey, what's your status, right? So let's do let's do some math here, a little bit of arithmetic. So that is a total of 11 seconds, right? 32:53 to 32:53 to 33:04. Oh boy, that is 11 seconds. So for 11 seconds, we're not getting any response from the JVM. So for sure, if a request had come in at this moment in time, whatever the service time is, it's going to be service time plus 11 seconds because the JVM just did not respond for 11 seconds, okay? So now, what is the net effect of that? Let me just undo this memory for a second and undo the classes for a second. And then zoom in and then line this up here. Okay, so you can see at the time 533.04, 533.04 right there. You see 533.04 is here, which matches up 533.04 here. So the time before that was 532.53, 532.53. Everything was fine. Okay, you say, well, look, the thread count is 314 at 532.53, and it's only 315 at 533.04. Well, remember, the JVM is doing cleaning, so it cannot really start new threads for you. The threads only started when the JVM resumes work. So when you look at this behavior here, it's not going to do a jump until after the JVM resumes work. So right after that, you can see there's a jump in thread right here from 315 to 378. Okay? That's the net effect. The JVM has to start 78 minus 15. So 63 threads. It has to start an extra 63 threads to accommodate that pause right there. But good thing for us is that look at this, 533.05, 533.34. So it basically took 30 seconds. So after 30 seconds, it resumes normal behavior. Okay, so the net effect, you know, if you look at it from 35,000 feet, all this says is, look, something happened, okay, and that something is 10 seconds. Really, that's not what you care about, because what you really care about is the number of threads down here. Something happened, and things just kind of get slows down for about 30 seconds, then it resumes normal behavior. And that's what you can say about this. All right, so going back to memory, what I want to see is what actually happened here. Because if you look at the trend here, rightfully at this moment in time, it should have just continued a normal behavior, okay? Well, if we zoom in, let's see what's going to happen. If you zoom in right here, you see this is 532.53. Rightfully, it should have just gone up just as the previous peak here, and then it would jump back down, right? But it didn't do that. Something actually happened that forced it to do a major cycle. I can guarantee you that this is a major cycle, because it took 11 seconds. And right away, the memory dropped down here. So it shouldn't have happened, but it did. Okay. So anyhow, if we want to turn this into a case study, what do we say about this? Okay. Well, I already know the answer because I worked with this case before. But the upshot is this behavior should not have happened. And that's basically it. So how to obtain more information to determine the root cause? Well, you already know that the delay occurred because of a garbage collection. Well, what that implies is that the only way to drill down to the root cause is to turn on the garbage collection flag, collect the garbage the GC log file, and then do the analysis on that. Okay, so that's it. So let's take a step back. The overall objective of this demo was to show you that in a graphing chart like this, if there's a lot of data, you cannot rely on what you see here. You really need to drill down to see the actual behavior. Okay, you can even drill down further, because when there's a lot of data, the graphing package will only do selective points and then try to draw all the straight line through to show you. Okay, so that's not a really accurate representation. So something for something that's more accurate, you need to drill down. Okay, so that's really the whole point. Now, to turn this into a case study, what I wanted to say is there is a jump, and there's a reason for this jump. The reason for this jump is the forcing of a major GC cycle. And this forcing is unfortunate because the number of service threads actually jumped more than the 20%. And it actually lasted, fortunately, only 30 seconds. But we did see a delay in service for about 30 seconds. We're looking at typical behavior of the ITSM stack. And this is divided into two sections. The typical JVM behavior for the web tiers, the mid-tier and the Smart IT. And then there's the typical JVM behavior for the AR servers. Okay, so first part that we're going to talk about is the web behavior, the mid-tier and the Smart IT. But really, there's two bullet items here. One is protocol server socket, and then the other one is thread count versus CPU. Okay, so let me go into the next slide and then I will explain a little more. Okay, if you read quickly over all the bullet points here, you see that it doesn't really have much to do with mid-tier or Smart IT. Well, the reason for that is because both mid-tier and Smart IT are web applications which run on top of Tomcat. So all the bulleted items here relate to Tomcat. Okay, so we're really looking at Tomcat. So the meta question would be, well, is this good enough if I can apply this to other Tomcat? Or maybe not a Tomcat, but other web servers? The answer is most likely yes. Other Tomcats, for sure. But other web servers may have different implementation, and it may not apply in exactly the same way, but the theory should still be valid. Okay. Every time I say connector in Tomcat, you think service. Okay. So for example, there's an HTTP connector. That is an HTTP service. There's an AJP connector. That's the AJP service. And you can say, well, I don't know what AJP is. Well, in the old days, AJP used to integrate into IIS and Apache. I don't know people still using that because Tomcat is very good at serving web pages now to static web pages. So most likely not. But unfortunately, it's on by default. And it is a security hole. So I will talk a little bit about that here. Okay, so for each protocol, oh, right, and there's also SSL because the HTTP connector corresponds to HTTP service, and then HTTPS connector corresponds to the HTTPS service, and the S just stands for HTTP over SSL. For each protocol service, there's a corresponding protocol server socket or listener. By default, you have 8080 for HTTP, 8443 for HTTPS or the SSL HTTP on top of that. Now, what do you see at the JVM layer? Well, it turns out that the people who coded Tomcat did a really good job. When they started a new thread, they name it corresponding to the connector. So that, for example, you always know how many HAP service threads are running, or how many HTTP service threads are running, how many HTTPS service threads are running, because you will see those as a prefix to your thread names. And I will show you the demo after this. So the service threads are started and killed based on the rate of requests coming in. And the point is, well, if you don't have a lot of requests, then why keep those threads around? okay? And then you can say, well, how many threads you keep around at minimum, or how many threads at maximum? Well, that's configurable, and that's inside Tomcat conf server XML file. And if you don't know much about that, you can Google and you can find out all the documentation for the server XML file. But we do have a KA to tell you the sizing and corresponding to the size of the hardware, how many threads to configure for what protocol in a KA, and that's in the reference section. Okay, so someone will always ask me this. Suppose I have absolutely nothing, just the baseline Tomcat. So can you tell me what it is so that I will know what the baseline is, so that when I deploy a web application on top of that, I will know how many extra threads there are. Well, there it is. For baseline Tomcat with no web app, minimal thread pool, it has about 20 threads running, and it uses about 30 meg of your heap. The point of the demo is to show you one extra tab that is called the Threads tab. And inside this Threads tab, I will select what's called live threads versus all threads. Let me go over to the Threads tab. Okay, when you go into the Threads tab, you can, if you click on this button, it will shrink everybody into the time frame. Okay, everybody will share the time. And notice that we're viewing all threads. Let me also sort them alphabetically. I think, yeah, that's much easier to see. Okay, so let me begin to name some items off here. Notice that HAP is running. You can see the HAP is running a service. Acceptor is a server socket on port 8009. And by the way, if you get your JVM snapshot and you look over the threads and you see HAP running, and you know for a fact that in your environment you don't need HAP, then you should go into the Tomcat server XML file and turn that connector off, because it really is a security risk. And also look at this. It took up a lot of resources because all these guys are related to HAP, when you can free everybody up so that the extra resources can go to other threads. Okay, so when I look at this chart, I only look at two colors. Oh, the legend is down here, and by the way, it's kind of hard to see, but anything that is green, green is running. I only see green, which is running. If it's purple, yellow, or orange, I just lump them into a single category. It's called wait or park or sleeping. Who cares? It means pause. And then monitored, which is pink, by the way, that means blocked. Okay, so those are the only three categories I'm concerned with. So when I look at these things, look at all these HAP threads. They're all orange. That means nobody's doing any work, because if they were doing some work, it would have been green. Okay, now of course the acceptor has to be green the whole time, because it has to be alive all the time to listen to the HAP request coming in. Okay, so remember, we're looking at all threads, so you will see this list is very, very long. So I can begin to scroll, and you see that's very long. Well, sometimes you don't want to see everybody. You just want to see, well, what are the live threads? When you click on live threads, only the live ones are around. Okay? So you can say, well, look at those HAP threads. If they're not doing work, why are they still around? Well, the answer is, look, let's count them. Look, there's 1, 10. So there are 10 of them. So anyway, the default for HAP connector is that always have 10 service threads hanging around. Okay, and that's why these 10 are here. Remember, if you don't use HAP in your environment, you can shut that off, and so all these guys will disappear. Okay, so let me just scroll down to the HTTP. So HTTP here, NIO stands for non-blocking IO library. So you can ask, well, is there a blocking IO library? The answer is yes. Up to Tomcat 7 is BIO, blocking IO library. That's a library underneath that deals with the actual socket. The reason for that was NIO was not really stable until Tomcat 8. So since Tomcat 8, everybody was standardized on using NIO. Okay, but the only thing that I want to point out here is all the pink. So notice all the pink here. You see all the threads here, they're all pink. Okay, and as I mentioned, pink meaning those threads are blocked. Okay, so they're blocked, they're not working. They want to work, but they can't because they're blocked. Okay, so that's the only thing I want to point out. So for this demo, the whole point was you can sort, you can zoom everybody into the same timeline. You can look at all threads, live threads, or just the finished threads. So when you see a jump in threads, you know right away that there's a reason for that. Well, it's a Tomcat. These are web applications. I can guarantee you that when you see a big jump in the number of threads, most likely the reason is because there's a huge number of service coming in, requests coming in. In our case, is the number of HTTP requests coming in. Okay, so if the number of HTTP requests are coming in, and all these threads are created to service those requests, then the expectation is that the CPU usage will also go up because CPU need to service all those requests. So the corollary is this: if there is a jump in thread count, but there's no jump in CPU usage, then we're encountering a problem. And this is very common. It's called bottleneck problem. Let's look at this. So everything looks pretty good up to here. And then, so notice the timeline here, about 212. Okay, so up to 212, everything looks pretty good. And then all of a sudden, there's a huge jump in thread counts. Now, in a normal environment, when there's a huge jump in thread counts, you expect to see a huge jump in CPU usage because CPU is necessary to service all those threads, or requests, or CPU time for all the threads. But this is not the case. Here, the number of threads are going up and up and up, but the CPU usage is going down and down. And I can tell you already that all the CPU usage here is just spent creating new thread instances. Okay, so then you can stop and say, well, there's a problem with this. And it sure is. When you look over here and notice that when you scroll down, all these HTTP service threads, they're there. There are thousands of them. Look by the number here, but they're all blocked. Blocked meaning they're not running. If they're not running, they're not using CPU. Okay, and so what's the reason? Okay, so at this moment in time, with this much data, this much info, the answer is we don't know. All we know is that all these HTTP service threads are blocked. And so you say, well, where do we go from here? Well, the next step is to look into the web application logs to see why these guys are blocked. Okay, so, well, not to keep you in suspense, but I can tell you the reason for this. One of the AR servers crashed. So all the AR API calls from mid-tier to the AR server is blocked. That's the answer to this scenario. We're going to talk about the typical JVM behavior of the AR server next. This is divided into three parts. The heap usage, the fast and list thread count. We already mentioned this at some point earlier in the talk. And I'm going to talk a little bit about slow external entities. Also, and the reason for that is sometimes when the AR server is slow, but it's not its fault. It's some external entity that's causing the slowness. Okay, so well, this next slide, there's a lot of data on here. Okay, the first thing you want to keep in mind is when you look at the JVM snapshot, you look at the worker threads, especially the fasten list, and by the way, these are named for you, so I will show you during the demo the fasten list threads. You want to make sure that these are never blocked. The fasten list threads, these guys access the database all the time. So they have to be rather quick, and you don't want to see any blockage for fasten list, because any blockage of any of those threads will remove them from service of the AR server application itself. Now, the next one I already mentioned. Make sure that your fasten list thread count configuration matches the 3 and 5x rule. And that's basically all I want to say. But I can show you that they will show up in the JVM snapshot. The third item, it's a tough one, because not tough, but most people will never come across and say, well, how do I know how many logical CPU there is? Well, if you look at the snapshot, it isn't displayed anywhere, but you can get the logical CPU count in the metadata of the snapshot. I will show you how to do that. Okay, and then the fourth bullet item. Someone always asks me, well, when I start the AR server, how many threads is normal, and how many threads is too much, how many threads is not enough? Well, the answer is, well, that's completely dependent on your hardware. If you have, for example, larger hardware, you have more fasten list threads for sure, and then that also depends on how many requests coming in, because you know, the AR server uses the MQ library, and that queue things up, and each of the queue has its own thread servicing the request there. So if you have large hardware with lots of requests coming in, the thread count is pretty high. Smaller hardware, less fasten list threads for sure, less requests coming in, less thread count altogether. So really hard to say. I want to give you an answer, but it's not safe to do that, so I will stay away from that one. Okay, but anything that is slow external to the AR server, such as a slow SQL query or slow DB response, will show up as a block state inside the AR server, and the block state is shown up in either fast or list depending which AR API you call. Now, I want to tell you one last item that is very, very difficult to trace. If it's an external block state, external to the JVM, you cannot see that. So you can ask, well, what do you mean? So for example, if a JVM thread is accessing a socket and is reading or writing to that socket, well, once it makes a call to the OS, says, look, I'm reading from the socket, then it's up to the OS to manage that. So inside the JVM, you just see green is running. So sometimes it's very difficult to say, oh my gosh, it took 2 minutes to read that payload and it's so small. Well, really, you can't say much about it. You just know that, well, it's reading from the socket, and the state of the reading from socket is external to JVM, so you don't really know. You just see it as green. Okay, so let's move to the demo here. Take a look and say, well, what's wrong with this? Okay, what's wrong with this? Well, the first thing I notice when I look at this is the GC happening here. Okay, and you can almost see the pause there. You see the straight line. I will zoom down to that. Okay, and then when you look over to here, you see that, well, you know, whatever that happened there, it shouldn't be happening here at all, right? Because that looks pretty normal. the heap is within the 1/3 to 1/2 range that I've described. So I don't know what's going on there, but one thing is certain. Look at the time there and look at the time down here. You can see already that the number of threads jump and it remained elevated for the entire duration. It never go back down again. Okay, so one thing you can say is, well, the AR server never caught up. Okay, so I'll tell you what the customer complaint was. It's they called and they say, well, everything works fine, and then it just started to slow down, and that was the end of that. And it slowed down for the rest of the day. I said, well, take a snapshot, send that to me, and I'll tell you what I can see. All right, so let me take a look at that moment in time right there, 120:25. Okay, so let's zoom in. Here it is. So here's at 120:27 and then 120:42. You can see right there the JVM stopped responding. Okay, and that's quite a long time. Well, I don't know, 35 seconds, right? And then in that 35 seconds, the number of threads jumped up here. Okay? And it remained elevated. It didn't go back down. If it had it gone back down to the same level here, I don't think the customer would have noticed really. The user would say, "Hey, we're slowing down a little bit," and then everything just resumed normally. So anyhow, let's take a look at what's happening. So the purpose of this demo is that we look into the threads, okay, to see what's happening over there. Okay, so remember, you can always click on this to zoom everybody into the same timeline and sort it. Okay, I'm going to sort this. And let me just take a look at the live threads because it's fewer. So let me go down and let me show you the fast and list. Notice it says pool fast, FTS, and pool list. So you can see that there are like 5 FTS threads, and there are 40 fast threads and 40 list threads. And you can say, hey, Hugo, this person here didn't follow the 3x, 5x rule. And the answer is yes. I think the 3x and 5x rule only apply up to a certain point. And then if anything larger than that, you just keep it at 40. I don't know. Look at the KA at the end of the reference. But that's just off the top of my head. Too much info to maintain. But remember, we were looking at this point right here at about 120, right? 120. And so when we look at this over here at 120, look what happened. You see all that pink? All that pink. Pink meaning blocked, okay? Well, good thing is just mostly the fast threads and not the list threads. Well, you know that you can look up the AR API list and see which API uses the fast thread and which API uses the list thread. Go to docs.bmc.com and do a search on that. I remember running into that at some point. So what can I say about this? Remember, the whole point was this. Something happened, the number of threads jumped, and the AR server never caught up. Okay, that was the whole point. Okay, so when I looked at this, I saw that at some point, all the fast threads were blocked. Okay, and when this happens, almost invariably is due to an external entity. Okay, and what external entity does fast threads utilize? The answer is almost always the DB. So I mentioned to this customer, say, you know what, at the JVM layer, I cannot tell you exactly what happened. You can go into the AR logs to look up, especially the SQL logs, to see what's going on in there. But I can almost tell you, I can tell you almost certainly that is due to something with your database. Your database just at some moment in time slowed down, and that affected all the fast threads. And the AR server never caught up with the workload. And that was it. That was all I can say with this JVM snapshot. Remember, the JVM is actually quite low level. It doesn't really know what's running on top, right? It's just a JVM, virtual machine, executing bytecodes. So to get a context, you do need to go into the application itself and look at the logs. So for this demo, with this particular snapshot, that was all the feedback I managed to provide to the customer. That something happened, most likely is an external entity, and that entity was most likely the database in slow in responding, and that caused an elevated number of threads, and the AR server never caught up with the work. Remember, your goal when you look at the snapshot is to make sure that the fasten list threads on that block, like that guy, pink. And if they all line up like that, is sometimes, most of the times, is some external entity. Okay, make sure the fasten list thread matches 3-5 rule. Oh, I'm going to show you the logic or CPU count in a moment. Thread count is dependent on the size of the hardware and your configuration. Anything external will show up as blocked, and if they all line up as I shown you in the demo, it means that it's an external entity. Okay, so let's take a look at this here. This is a snapshot. I map it. It's actually a zip file, so you can unzip it, or I map this to WinRAR, so you double click and WinRAR opens up. And here's the application snapshot properties. I remapped this to my notepad, so when you double click, it opens up in notepad. If you scroll down to the very bottom, you can see the number processor here, and it says that this JVM was running on 4 processor. Now remember, the JVM is running inside some OS, so it's too high level to really know whether this is actual physical or logical. So the answer is you can treat that as 4 logical CPUs, and that's all you can say. Troubleshooting essentials. It's a nice point in time to recap what we had discussed so far. Well, the first part is the CPU and GC. The basic rule is the usage should not exceed 80% for longer than 30 seconds. And the reason for that is if you have an application that's running as a service, it has to service not just one user, but many, many users. And when you have CPU usage exceeding 80% for longer than 30 seconds, some users will suffer, and they will complain, and you will hear about that. I did not put anything about the GC, but remember, typically you want 5% for GC, and if there's a pause, below 3 seconds acceptable. You know, even 15 seconds, okay, if it happens once in 24 hours. If it happens more frequent than that, you do need to get the GC log and do some analysis. And that is a highly specialized skill set, this whole garbage collection. Now, next we go into the heap. With a range allocation, not much I can say because the heap goes up and down. But with the fixed allocation, what we want to see is 1/3 to 1/2 free all the time. Okay, 1/3 to 1/2. That's a good rule of thumb. Okay. Now there are cases, there are exceptions where you see less than 10%, but then after that something should free up, and you have to go back to your 1/3 to 1/2 rule right there. And last, for the thread count, basically you want what the normal condition is. Plus minus 10% is perfectly good. If it's more than 20%, you should look into it. And if it does go up and it catches up, then you're fine. If it goes up and it stays up, that's not good. You should look into details. Okay, so for the troubleshooting or extra case studies, I thought, well, first, why don't I show a picture of what a typical AR server behavior looks like while it's running and while it's resting. So here, this happens. This was the most beautiful run. All the use case times were optimal, no problem at all. So you can see here, the load was running the entire time. Okay. Now you can say, well, that's a pretty light load, right, Hugo? Because when you get real customers, don't they go up here? Well, the answer is yes and no. It turns out that when we do the sizing based on the hardware, like we normally, so for example, if a new customer wants to build up a production environment and they get me in to consult on the sizing, I would say, well, typically, if you have 300 users using the following set of use cases with this many tickets per hour and this aggregated to this many tickets per day, this is the size of hardware. And that's the type of benchmark we run. And it turns out that based on our benchmark, our prediction, this is the behavior. Remember, in a lab, things are more controlled. So this is a load that is generated by was generated by Silk Performer. It doesn't have the variation of an actual end user load, which is more unpredictable. So this is behavior during the load, and this is behavior during rest. You can see right away the garbage collection was really good. All the minor cycles really quick. Everything goes up, back down right away, and you have that 1/3 to 1/2 rule right there. Now during rest, you can see that Heap usage is still being used during rest, right? That's because the AR server is running all the time, right? There's a lot of tasks like escalations going on in the background, FTS going on, indexing going on. So you do see that the Heap is being used. Okay, and the best part about this is the number of threads. Notice that throughout the load and the rest, it's constant within that 10% mark I mentioned. Next. Oh, the environment is perfectly fine, like Mondays and Tuesdays, and by Wednesday it kind of slows down a little bit, and then Wednesday evening we kind of have to restart, okay? And we don't know what's going on. The logs didn't say much. All right, so then they asked me to work on the case, and I said, okay, if I were to work on it, so why don't you do this for me? When, let's say Wednesday, right? Just start the JVM monitoring, and then after the slowdown happens, just wait for 10-15 minutes, take a snapshot and send that to me. And they did, and this was what I saw. And they didn't have to do long, and you can see right away the JVM stopped responding. Whenever you see jaggies, that means that the JVM stopped responding, and the data aggregation here is doing interpolation, and it does the simplest interpolation, which is a straight line, right? So anytime you see jaggies, you can see the JVM is slow in responding. And you look over here, and right away you see there's a problem, and you say, wow, that is 20 gig of memory, and yet they're running out. Wow, this was a huge customer. They have like 120,000 different groups, and this was the reason. Let's go to the next one. Okay, I threw this in because this was one of those cases where I didn't have an answer. It's an AR server, and it was on a host OS issue. So here's the monitor and the snapshot, and everything was fine. They say, oh yeah, there's a little bump there, but that was fine. But they didn't know what happened here. So you see, there's a jump in thread and stayed up like that, okay? And when you look at this heap, you know what? Look at this. Everything is just fine. And this looks like it can go on forever, right? And everything over here looks fine too. So they asked me, look at this jaggy. So I noticed that jaggy right away. That jaggy right there. Let me zoom in on that. And then we can take a look at that. So let's take a look at this jaggy right here. Okay. So it was 7:23:34. From 23:34 to 24:06, that's 32 seconds. The JVM stopped responding. Okay? And for 32 seconds, well, the thread jump wasn't too bad, by the way. I mean, so it's 464, 65 to 520, 65. I don't know. If it's not more than 20%, I wouldn't be too worried about it. But really, they took the snapshot and all they wanted was an answer to why it happened. And when I saw this, I thought, well, let's take a look at this. Over here, let me zoom in. And you can see right here that there's no reason. You can see that is a natural minor cycle. Okay, if you read enough GC log, you see that every of these little tiny jaggy corresponds to a minor cycle. So corresponding to minor cycle, that's happening all naturally, you see, but it took forever to do this, a whole 32 seconds. And they asked why that is. And the answer is, I don't know. This is a natural minor cycle. It should have taken 1 second and everything would have been fine. So this was one of those cases where at the JVM layer, even though you have the snapshot data, there was no answer, no good answer that can be deduced from this set of data. So you need to take a step back and say, well, the JVM is running on a virtual machine or a physical machine. Physical machines are much better because, you know, behavior is expected. But if you're running on a virtual machine, which like almost everybody, I don't even know of a customer that's running on a physical machine anymore. So on a virtual machine, you have a virtual emulation layer, and anything could have happened there. So I asked them to look at the tooling for the virtual machine layer to see if there's anything that happened at that moment in time, because from the JVM layer here, I have no answer. Okay, so that's the end of that demo. Okay, now for the last item, this is inside the mid-tier, there's the EH cache. And when the EH cache slows down, the service time, it's not good. It's not optimal. And I just want to show you a picture of a snapshot where you can spot that the EH cache is misbehaving and give you some basic rule for that. Okay, well, anyway, this was really heavily used, by the way, as you can see by the number of threads here. Everything was normal, except the timing was not optimal for the use cases. So let me zoom everybody in. Do this, but let me just show you only the live threads. If you just look at only the live threads and go all the way to the bottom, you will see the EH cache threads. Each of these corresponds to an EH cache store. And the basic rule of thumb is this. Over the duration, the usage should be below 10%. Now, if you want complete optimal use case service time, you would shoot for below 2%, but anything below 5% is good, okay? So if someone sent me a snapshot, I looked at it, and if everything's below 10%, I don't even want to suggest any changes because the end users probably won't notice anything. But really optimal use case times less than 2%. Okay, the rule is 2%. And I see that right here, the store for the ref count was at 65%, and the sync relationship was at 57%. And then I say that this EH cache here needs some fine tuning. Okay. Here are the set of references. If you want just a quick JVM monitoring, go here. For the KA, this is, by the way, that's the standard reference that I myself use, 10,000 concurrent users benchmark, and I had to fine tune a lot of stuff, and everything that I did was in here. And then there's a performance tuning white paper, and that's there. So it's a good set of references in one location for you to look at, and that's the whole thing.
Now I will take us through the closing, some self-help in contacting BMC. Our videos as well as this webinar recording are available via our YouTube channel. Once this information is posted, it is reflected in our Connect with BMC Helix ITSM and Remedy schedule, available at this communities link, as well as the product support pages that contain different videos, documentation, knowledge articles, combined based on product component. A very useful resource available 24/7. And as always, our technical support methods of contact via web, phone, and email, as well as the social channels as well. Thank you.